Today we're going to explore a fascinating intersection of science and art, how microfluidics is revolutionizing the way we create, mix, and apply colors in artistic applications. First, let's understand what microfluidics actually is. Microfluidics is the science and technology of manipulating fluids at the microscale, typically dealing with volumes in the microliter to picoliter range. Imagine tiny channels, thinner than a human hair, etched into materials like glass or plastic. These channels can be as small as 10 to 500 micrometers wide. That's about 1/10 to 1/2 the width of a human hair. Let me give you some perspective on these scales. How small are we really talking about? 1 microliter is 10 to the negative 6 liters. That's 1/1,000,000th of a liter. 1 picoliter is 10 to the negative 12 liters. That's 1/1,000,000,000th of a liter. Here's a back-of-envelope calculation. A single droplet from an eyedropper contains about 50 microliters. Microfluidic devices can control volumes that are thousands of times smaller than this. Now you might ask, why do fluids behave differently at the microscale? This is where the physics gets really interesting. At the microscale, surface forces like surface tension and viscous forces dominate over gravitational forces. This is because surface area to volume ratio increases dramatically as you shrink down. The Reynolds number tells us about fluid flow regime. It equals density times velocity times characteristic length divided by viscosity. In microfluidics, Reynolds numbers are typically less than 1. This means flow is laminar, not turbulent. Laminar flow means that fluids flow in parallel layers with very little mixing between layers. Two fluids can flow side by side without turbulent mixing. Picture two different colored fluids flowing through a microchannel. Red and blue streams flow side by side in beautiful parallel layers. They don't mix chaotically like they would in a larger pipe. Let's explore the first major application in art, precise color mixing. Traditional color mixing on a palette can be imprecise and wasteful. When artists mix colors on a traditional palette, they often make too much or too little, and achieving exact color ratios can be challenging. Microfluidic systems can mix pigments with nanoliter precision. This means you can create exact color gradients and reproducible shades. Imagine you want to mix red and yellow to get the perfect orange. With microfluidics, you can control the exact ratio, say 50% red and 50% yellow, down to the nanoliter scale. Let's do a quick calculation to see how much paint microfluidics can save. Traditional mixing might use about 5 milliliters per color test. A microfluidic system might use only 1 microliter per test. The savings factor is 5 times 10 to the negative 3 divided by 1 times 10 to the negative 6, which equals 5,000. That's 5,000 times less paint needed for each test. The second application is creating microscopic color patterns on canvas. This opens up entirely new artistic possibilities. Microfluidic printheads can deposit pigments with pixel-level control, creating patterns and textures that are impossible with traditional brushes or even conventional printers. Picture a canvas where each tiny dot of color is precisely placed. These dots can be as small as 10 micrometers in diameter, invisible to the naked eye but creating rich textures when viewed as a whole. How does this compare to human vision? Let's think about resolution. The human eye can resolve details down to about 100 micrometers at normal viewing distance. Microfluidic droplets can be 10 to 50 micrometers in diameter, which is at or below the limit of human perception. This creates optical mixing effects, similar to the pointillism technique used by artists like Seurat, but at a microscopic scale. The eye blends the colors together, creating smooth gradients and rich hues. The third application is creating smooth color gradients and ombre effects. These are notoriously difficult to achieve uniformly with traditional techniques. Creating smooth gradients traditionally requires skilled hand blending and multiple layers of paint. It's time-consuming and difficult to reproduce. With microfluidics, you can create perfectly smooth gradients by varying the flow rates of 2 or more pigments. Red gradually transitions to blue by continuously adjusting the ratio of red to blue ink flowing through the channels. You might wonder, how exactly does varying flow rate create these gradients? The fraction of red color equals the flow rate of red divided by the sum of red and blue flow rates. By smoothly decreasing the red flow rate while simultaneously increasing the blue flow rate, you create a continuous gradient. The microfluidic controller can adjust these rates with millisecond precision. Let's work through a concrete example. Say we want a linear gradient from pure red to pure blue over a 10 centimeter canvas. The red flow rate, as a function of position, equals Q0 times 1 minus x over L, where L is the canvas length. The blue flow rate equals Q0 times x over L. At x equals 0, you have pure red. At x equals L, you have pure blue. In between, you get a smooth linear gradient. The fourth application involves encapsulating pigments in microdroplets. This is where microfluidics becomes truly revolutionary for art materials. Using microfluidic techniques, individual pigment particles can be encapsulated in tiny polymer shells. This protects the pigments from degradation and allows controlled release. Picture a tiny sphere with a polymer shell on the outside and concentrated pigment on the inside. The shell protects the pigment from oxidation, light damage, and chemical reactions. Let's estimate how many of these microcapsules would be in a single brushstroke. Assume each capsule has a diameter of 50 micrometers. A typical brushstroke might contain about 10 microliters of paint. The volume of one capsule is 4/3 pi r cubed, which equals about 6.5 times 10 to the negative 5 microliters. The number of capsules is 10 divided by 6.5 times 10 to the negative 5, which gives approximately 150,000 capsules in a single brushstroke. The fifth application is using microfluidics to control paint viscosity for different canvas textures. This is critical for how paint flows and adheres to different surfaces. You might ask, why does viscosity matter so much in painting? High viscosity paint is thick and creates visible brush strokes. This is used in impasto technique where texture is part of the artwork. Low viscosity paint is thin and flows smoothly, creating watercolor-like effects with soft edges and gradual transitions. For rough canvas with lots of texture, you need lower viscosity paint that can flow into the crevices. For smooth canvas, higher viscosity paint sits on the surface and maintains texture. Microfluidic systems can adjust viscosity in real time by mixing concentrated pigment with varying amounts of solvent or binder. This happens automatically as the paint flows through the channels. The ratio of thick to thin paint viscosity can range from about 100 to 1000. Microfluidic mixing can achieve any value in this range continuously. The sixth application is creating metallic and pearlescent effects. These special effects require precise alignment of reflective particles. Metallic and pearlescent paints contain tiny flake-shaped particles, often made of mica or aluminum. The orientation of these flakes determines how light reflects. In microfluidic channels, the shear forces from laminar flow naturally align these flakes in preferred directions. This creates more uniform and controllable metallic effects. As the metallic paint flows through the microchannel, the flakes align with the flow direction, creating a consistent orientation that produces uniform shine and reflection. Let's understand the physics behind this particle alignment. The shear rate, represented by gamma dot, equals the derivative of velocity with respect to position perpendicular to flow. The particle rotation rate omega is proportional to the shear rate. Higher shear rates cause faster rotation and better alignment. In microfluidic channels, shear rates can exceed 10,000 per second. This is much higher than achievable with traditional mixing, leading to superior particle alignment. The seventh application is multi-layer painting with precise thickness control. Classical techniques like glazing require building up thin, transparent layers. Traditional glazing requires applying thin layers by hand, waiting for each to dry, and hoping the thickness is consistent. This process can take weeks for complex paintings. Microfluidic systems can deposit layers with nanometer scale thickness control. Each layer can be precisely metered and applied uniformly across the entire canvas. Imagine building up a painting with 3 colored glazes. The first layer is exactly 10 micrometers thick, the second 5 micrometers, and the third 5 micrometers. This precision creates optical effects impossible with traditional methods. Let's calculate how thin we can make a layer while still having it affect the appearance. Visible light wavelengths are around 500 nanometers. The minimum layer thickness for an optical effect is about wavelength divided by 4 times the refractive index. Assuming a refractive index of 1.5, this gives about 80 nanometers. Microfluidic systems can easily achieve this level of control. The eighth application is reactive color systems, where paints change color based on environmental conditions. This is where art meets chemistry. By encapsulating pH-sensitive dyes in microcapsules, you can create paints that change color when exposed to acidic or basic conditions. The capsule protects the dye until deliberately broken. Thermochromic pigments change color with temperature. Microfluidic mixing allows precise control of the transition temperature and color range. Imagine a painting that is blue when cool, but turns red when warmed by a viewer's hand or by sunlight. This creates interactive art that responds to its environment. What's the chemistry that makes this possible? Many thermochromic systems use leuco dyes that exist in two chemical forms, a colored form and a colorless form. Temperature shifts the equilibrium between these forms. The colored form is in equilibrium with a colorless form. Temperature determines which form is favored. With microfluidics, you can mix multiple reactive systems in controlled ratios. For example, one capsule system responds to temperature, another to humidity, creating paintings that change in complex ways. The ninth application addresses sustainability. Art materials production can be wasteful, but microfluidics offers solutions. In traditional paint manufacturing, roughly 10 to 20% of materials are wasted during mixing, transfer, and cleaning processes. Microfluidic systems can produce paint on demand, mixing only exactly what's needed. The small volumes mean cleaning requires minimal solvent, and there's virtually no waste. Let's calculate the solvent savings from using microfluidic systems. Traditional equipment cleaning might use 100 milliliters of solvent per color change. A microfluidic system might use only 0.5 milliliters per color change. For 50 color changes in a painting session, that's 5,000 milliliters for traditional versus 25 milliliters for microfluidic. That's a 200-fold reduction in solvent waste. The 10th and final application is translating digital art directly to physical canvas using microfluidic printheads. This bridges the digital and physical art worlds. Traditional printing technologies like inkjet often lose the subtle color nuances and texture of digital artwork because they use limited color palettes. Microfluidic printheads can mix any color in real time from a small set of primary pigments. This allows faithful reproduction of digital colors with millions of possible shades. A digital image is analyzed pixel by pixel. The microfluidic printhead moves across the canvas, mixing and depositing the exact color for each position. The result is a physical painting that perfectly captures the digital original. What about resolution and printing speed? Modern microfluidic printheads can move at 10 to 50 centimeters per second. They can deposit droplets at frequencies of 1 to 10 kilohertz. That's 1,000 to 10,000 drops per second. For an A4-sized canvas with high resolution, printing time is approximately 10 to 30 minutes, comparable to traditional printing, but with far superior color accuracy. Let me summarize the revolutionary impact of microfluidics on art. Microfluidics brings unprecedented precision to color control, allowing artists to work at scales and with accuracy impossible with traditional methods. From precise mixing to controlled deposition to reactive color systems, microfluidics is transforming every aspect of how we create and experience art. The sustainability benefits are enormous, reducing material waste by factors of hundreds or thousands. This beautiful intersection of science and art demonstrates how deeply physics, chemistry, and fluid dynamics can enhance human creativity. As we conclude, ask yourself, what other applications of microfluidics in art can you imagine? Could we create paints that respond to sound, pigments that change with humidity? The possibilities are limited only by our imagination and understanding of the science.